Hello, my name is Sultan. I'm a postdoc at the Physics of Fluids group at the University of Twente, and today I'm going to talk about Elastocapillary Worthington jets. This is a work that I've done together with Detlef and Masi. The motivation of this work arises from a number of applications involving droplets of polymeric solutions impacting on substrates, such as pesticide treatment of plants, where you use polymers to change the droplet size distribution, or inkjet printing, where you add polymers to suppress satellite droplets. And in all of these applications, the droplet has to impact on a substrate at some point. So the question is, essentially, how is the impact behavior altered by the addition of polymers? And what these polymers do is effectively add viscoelasticity to your liquid. So the question is, how is the impact behavior altered by essentially the addition of viscoelasticity? To do so, we develop a very simple experimental setup. We have a droplet impacting on a superhydrophobic surface. We're going to look at it from the side with a high-speed camera. The non-dimensional numbers of importance are the Weber number, which is the ratio of the inertial stresses to the capillary stresses, given in this form here, where U0 is the impact velocity, D0 is the droplet diameter, rho is the liquid density, and gamma is surface tension. And the Deborah number, which is the ratio of the relaxation time of the polymers to the characteristic time scale of the system itself, where lambda again is the relaxation time of the polymers, and tau gamma is the inertial capillary time scale given in this form here. And we're going to look at the regime map in this Weber-Deborah phase space. So what are the typical regimes that we observe? We have the classical rebound of a droplet on a superhydrophobic surface, as shown here, with a droplet impact, it spreads and it rebounds. And in the Weber-Deborah phase space, this is where it lies. There's the partial rebound regime, where the droplet impacts, a part of the droplet leaves the substrate while the rest stays pinned. And within this part of the droplet that is leaving the substrate, we can sometimes observe these beads on a string kind of structures that are formed. So we call this regime the partial rebound plus beads regime. We have the deposition regime, where the droplet lands and kind of just sits there without doing anything. And finally, we have the deposition plus beads regime, where the droplet lands, it forms this Worthington jet here, and within this Worthington jet, we see the formation of these beads on a string structures that are appearing. And these are all our experimental data points. We are going to focus mostly on this regime here, and we're going to ask ourselves the question, what is so special about the Worthington jet in this regime? We're going to look at the jet dynamics. So this is how a typical experimental snapshot looks like, and we're going to measure this jet length from this experimental snapshot. So this is how a typical measurement looks like. So as the jet length first increases, it will reach a maximum, and then it starts decreasing after that. And going forward, what we're going to do is we're going to focus on the jet stretching. So we are only going to look at whatever is on the left-hand side of this red line here. And we're going to shift our time axis to this point here, where the jet first starts appearing. And this is a typical measurement of such nature. And these are all our measurements for the deposition plus beads regime that I just showed. And within the same Deborah number, we also have the deposition regime at lower Weber numbers. And this is how those measurements look like. So right off the bat, you can see that to form beads, you need longer jets. We are going to normalize our lengths and times. So we normalize our length with the droplet diameter and normalize our time with the inertial capillary time scale. And this is how the data looks in the normalized space. We're going to look at uniaxial stretching of the jet. And for uniaxial stretching, the strain rate is given as epsilon dot, given in this form, where what we do is essentially we take the scale of U to be LJ dot and scale of Z to be LJ. And this is how a typical measurement looks like. And these are all our data points. And we're going to focus on the region where the slender jet approximation is valid. So that would be the cases where before all the curves have the sharp decrease. So this is how the curves look like. And if we take another derivative of our epsilon double dot, this is how they look like. And you can already see for the deposition plus beads regime, at early times, we have this value of epsilon double dot that's almost independent of time, as I showed here with this black box. So the question is, can we explain this? So to do so, we construct a very simplified model where we look at the jet in the axisymmetric configuration for any cross-section on the jet. The tensile force is the sum of the capillary stress plus the polymeric stress here. And at the base of the jet, the rheological stress is negligible. So it's only the capillary stress here. And equating these two, we get an expression for the polymeric stress just from the dynamics. And we're going to confine our analysis to dilute polymer solutions. So essentially, we're going to neglect viscosity. And for a slender cylindrical filament, this is how the strain rate components look like. So this is the strain rate components for a slender cylindrical filament. We are going to model the polymers in the Finney-CR model, where there's assumed to be two beads connected by a spring. And we use the slender jet model for the dynamics of the jet itself. And this is how the polymer stresses are written, where EC is the elastocapillary number given in this form here, where G is the elastic modulus. So the polymer stress is given in this form here. So, and this is the expression for the polymer stress that we get from the constitutive equation. So we have the expression of the polymer stress from the constitutive equation, and from the dynamics itself, we can equate these two terms to get this expression. We're going to make some more simplifications now. So we're going to look at the limits of infinite extensibility, because our jet never breaks up for the cases we are studying. So we can actually put in these assumptions in our expression here to simplify our equations to these two equations here, where this is the jet dynamics and this is how the conformation tensor AZZ varies. Now we have these two equations. Now we can assume that polymers are unstressed at the base of the jet, which allows us to write this, and which allows us to actually simplify this expression to get this expression for the exponential decay of the polymer stress, which is what one expects to have for pure thinning. And we can substitute this here to get this expression here. Now, this is a nonlinear ODE. We can solve this numerically with this initial condition. And so this is the equation we're trying to solve. I'm going to remind you that we're looking for solutions at the strain rate, which is expressed in this form here. So this is again the strain rate as a solution of this equation here. And we are going to do a linear approximation. And the linear approximation is a reasonably good fit. And what does this tell us? Well, these are again our data points from the experiments. And we are going to do a linear fit to each of these lines. These are these dashed lines here. And you can probably see already that for the cases where there are beads, which are the rate data points here, the linear fits are very good at approximations. And whereas for the deposition regime, where there are no beads, the linear fits are not really that good. So the linear approximation works very well for the deposition plus bead regime, but not for the deposition regime. And this linear approximation, I remind you again, is the linear approximation of epsilon dot as a function of time. So what does this show us? That our experiments showed that epsilon double dot is independent of time at early times, which means epsilon dot is linear in time. And that's also what our idealized theory suggests. And now, if I remind you, our theory had no inertia in there. It was only elasticity and capillarity. So essentially it shows that our Worthington jet enters the elastocapillary regime for the cases where there are beads on a string being formed. And this is not traditional, because traditionally Worthington jets have always been inertial capillary. So this is a new finding in a sense. And this elastocapillary Worthington jet is characterized by the strain rate being linear in time. But once in this elastocapillary regime, the nonlinearities will result in the formation of the beads, as I studied by these two papers here for pure cylindrical jets. But to do so, we need pneumatics, which is not something we did in the present work, but we're progressing on it as we speak. So to summarize, we identified different regimes for drop impact of viscoelastic liquids and superhydrophobic surfaces. We identified that for a certain Weber and Debra number, the Worthington jet develops these beads and string structures because the Worthington jet is now in the elastocapillary regime, and within this elastocapillary regime, the strain rate is linear in time. This is also predicted by a very simplified slender jet theory. With that, I want to thank my co-authors and my sponsors. I want to thank the audience. If you have any further questions, you can look at the preprint on arXiv, or you can talk to me or send me an email. Thank you.